let me add some intuition to this by stating the following. So what is the space V cross V tensor W? Is the space spanned by things like this. So with these rules, here comes the sort of thing that puts it all, in a sense, together. If E1 up to En is a basis for V, and F1 up to Fm is a basis for W, this set of things, EI tensor Fj, and how many of them are there? There are n of this and m of those. This, for I from 1 up to n, j from 1 up to m, form a basis for V tensor W. So basically, if you have a 4-dimensional vector space V and a 10-dimensional vector space W, V cross W is 40-dimensional. You multiply the dimensions. You don't sum them. In the tensor product, the dimensions multiply. Each, you see, the elements of this tensor product was one vector here, one vector there. So it behooves you that you would expect that, well, you can get all vectors that can sit here with all the EIs, all the vectors here, but only if you have these rules of superposition and linearity. So this is the whole basis of the vector space. And dimension of V cross W would be equal to the dimension of V times the dimension of W. Okay. Questions? Yes?
So for the first box thing up there, so V and W are two different vector spaces. How do you know that alpha W, let's say that they're vector spaces over different fields. How do you know
Oh, no, different fields, no. Both are over complex numbers.
Okay, they're both complex. Okay.
Oh, yes, yes. Both spaces are complex vector spaces. Did I say it? Complex vector space, then V cross W is an element of a new complex vector space. So yes, everybody's complex here. One second. Okay, let me continue a little more because we need to get a little further. I would like to get a little further here today. We still have about 10 minutes. These are really, in some way, simple, but in some way, very subtle ideas. I hope you appreciate that. At some moments you think, oh, this is obvious, it's ridiculous, it's taking too long to explain it. At some point you step back and say, oh, I'm now confused. What does that mean? You know, it's very easy to sort. It is subtle. So let's see now what happens. We need to do operators on V cross omega. So suppose T is an operator in V, and S is an operator in W. So we call them like that, T's, operators on V, S, operator on W. So here it is, we define an S tensor T that will be an operator on the tensor product, V cross W. Let's see how it is. So if this is an operator on the tensor product, it should know how to act on V, any element. in any basic element or element of this form, since all the elements can be written as superposition of these things, if this is a linear operator and I define it acting on this, we've got it. Now, what I'm going to write in the right-hand side is a matter of common sense. It's a definition, but it's hardly possible to have any other definition of what I'm going to do. You know, oops, what's wrong here? Lights, main screen, window shades, main screen. Oh, lights here. There we go. Well, you know, I got the order wrong here. T cross S. And the only thing you could do is if T, you know how it acts on V, well, let it act on V. And it will be a vector in V. And you know how S acts on omega, so let it act on omega, and that's the definition. Not that complicated, really, in a sense. Each operator acts on its thing. So you just let it act. Whoever has to act acts wherever it can do it. And it's linear operator, and you know, if you act on more things, it will be linear. It will all be fine here. Now, this is a fine operator. Now, the operators that are a little more surprising, perhaps, at first sight, are the following. Suppose you have an operator T1, that it's an operator on V. And you want it to act on the tensor product. Well, you say, oh, well, I need another operator. This acts on V. I need another operator that acts on the tensor product. But you don't give me one. So what am I to do? So this is what it's called upgrading an operator that acts on one vector space to an operator that acts on the whole thing. Because you need everything to act now on the tensor product. So what you do is the following. You let the operator become T1 that acts on V, and you put tensor product with the identity operator. So this is more or less what you would imagine. You have now an operator that belongs to the linear operators on the tensor product, but it's the operator you got times that. If you had an operator S1 belonging to L of W, it would go into 1 times S1. Now I ask you the question, do these operators commute? Strange question, but it's a fundamental question. It's really the basis of most of your intuition about two-particle systems. Well, let's see if they commute. You have T1 tensor 1 multiplied by 1 tensor S1. It's going to act on V tensor W. Or you have it in the other order, 1 S1 T1 1. Well, the first one, when it acts, the first part, it gives me T1 tensor 1. But now acting on this is V tensor SW. And then when I act on this one, I get now T1 on V tensor S1 of W. And when I act here, the first step, it gives me a T1 on V. And the second gives me the S1 on W. So it gives me the same thing, T1 on V S1 on W. So these two operators, because they originated, they're operators of the first particle, operator of the second particle, they can act on the whole system, but they still commute. They don't know about each other. And the commutation now is a calculation in which you just have seen it. So what is a good example of this thing is that when you try to write the Hamiltonian of the whole system, H total, you would say, oh, it's the Hamiltonian of the first system, tensor 1, plus 1 tensor the Hamiltonian of the second system.